Okay, so let's try to discuss this chapter, dual nature of light. Light has got dual nature, that is particle nature as well as wave nature. So both these natures coexist within light. Particles of light are called as photons. Energy of each photon is given with the formula E equals to h nu, where h is your Planck's constant and nu is your frequency. Frequency of any wave is given as speed of the wave by its wavelength. Here c is the speed of light, lambda is its wavelength. Now while doing calculations, we can always write the fixed value of Sc, which is 1240 electron volt nanometer or 12400 electron volt Armstrong. If lambda is given in terms of nanometer, we can use this formula to get the energy in terms of electron volt. If lambda is given in terms of Armstrong, we can use this formula to get the energy in terms of electron volt. 1 electron volt is always 1.6 10 to the power minus 19 joules. Now momentum of each photon is given by the formula E equals to mc square. Now E is basically mc square. So when we divide by c, we will get m into c. Mass into velocity is momentum. Now that's why the formula is P equals to E by C. Now E is sc by lambda. If we place this formula here, C and C will get cancelled and we'll get P equals to H by lambda. Now, as per de Broglie's hypothesis, the same formula can be used to calculate the wavelength of even material objects. So lambda is given by h by p, where p is the momentum of the material object there. Now for any material object, p is given as mass of the body into v. V is the speed. So p square will be this. Here we divide and multiply by 2 and we take 1 m outside. So we get half mv square, that is kinetic energy. So we get p square equals to 2 mk. So p is under root 2 mk. We can put the value of p back in this formula. So we'll get lambda as under root h by under root 2 mk. Now k is work done. Work done is given as charge into voltage. For electron, h, m, q, everything is fixed. So if we write all those values, we'll get lambda as 150 by root v. The 150 root of 150 is given as 12.27 angstrom. Same thing can be done for even proton, alpha particle and deuteron. I have written the respective values of lambda for the different cases. Now a photon collides with a reflecting surface. So let's see how we calculate the pressure exerted by this photon on this reflecting surface. P is the momentum of the incident photon and it gets reflected with the momentum, let's say p vector. So now initial momentum, if we resolve, we'll get two components of momentum like this, and after collision, if we resolve this, we'll get two momentum like this, two components of momentum like this. We can see that the vertical component of the momentum remains same before the collision and after the collision. There's no change in momentum in the y direction. Along x-axis, you can see that initially the momentum was in this direction, that is towards the negative x-axis, and after collision it is towards the positive x-axis. So final minus initial, if we do, we'll get 2p cos theta I cap. Change in momentum itself is called as impulse. Force is given by impulse by time. So we can put this value and we can get the impulse. Now pressure is force upon area. So we can write this force, delta T, have written here T. Now P of photon is given by h by lambda. So I can add h by lambda here. Now if we multiply and divide by c, so this h c by lambda is basically energy. So energy by time by area. Energy per unit time per unit area is your intensity of the photon. So the pressure exerted by the photon on the reflecting surface is given by this formula. Now photoelectric equation. Whenever a photon is incident on a photosensitive metal plate, the Kmax, the maximum kinetic energy of the coming out of the emitted electron, is given with this formula, Kmax equals to E minus a work function. While doing the same thing experimentally, if you want to stop all the photoelectrons from moving from one plate to another, you have to apply a voltage, and the voltage has to do a work equals to E into V naught, where V naught is the stopping potential. This Kmax can be written in terms of frequency like this. This Kmax can be written in terms of wavelength like this. Nu is a frequency, so A is h nu. If we incident the frequency, if we incident the photon in such a way that it is equals to work function itself, then that frequency is called as threshold frequency, h nu naught. Obviously, if I place these two values back here, if I take h common, I will get nu minus nu naught. So in order to have k max, nu should be greater than nu naught. Similarly, if we want to write this equation in terms of wavelength, we will write E equals to sc by lambda. If I place this value back here, and then if we incident the photon in such a way that its wavelength is such that we will match that energy with equals to this work function itself. So in that case, there will be no photoelectrons here. And in this case, in order to have k max as positive, lambda should be less than lambda naught. Now let's discuss the different graphs that we have in this. E equals to h nu. So the graph between E and nu will be a straight line. Sc by lambda, so it's a rectangular hyperbola. P h by lambda, again rectangular hyperbola. P square equals to mk. It's a parabolic case. The concavity of the parabola is always towards the linear power of the variable, so that is k. So if k is this side, concavity will be this side. If k is in this side, concavity will go this side. If I draw between p square and k, then I will get a straight line. If I draw between p and root k, again I will get a straight line. This is the Einstein's photoelectric equation. So if I draw the graph between k and frequency, I will get straight line. Even if I change the metals, since the slope will remain the same, so all the lines will be parallel. Same thing can be done even for lambda. At this point, I have written nu naught. The reason is, at this frequency, k max is 0. We know that the incident frequency for which k max is 0 is called a threshold frequency. This is nu naught. Similarly, when we study photoelectric effect, this is the graph that we get. Now this is stopping potential. Now in this case, we are keeping the metal same. We are changing the light incident on the photosensitive metal plates. So now, since the stopping potential is same for all the cases, it means that the frequency of the incident photon is same. Now, since the saturation current is different in all the cases, intensity of light is different in different cases. If we have more intense light, we will have more photons hitting the surface in a given time, so it will take out the probability. It will take out more electrons from the surface, and hence we will have more current. So we can say that intensity I1 is greater than I2 greater than I3. In this case, stopping potentials are different. So we can say that here the frequency of incident frequency is more than this. So nu1 greater than nu2 greater than nu3. Since this is constant, therefore we can say